Okay, in this video we're going to be talking about trig identities, so solving different equations, not solving them, simplifying different equations to get them to match and simplify them to be either one sine, cosine, or tangent instead of having multiple sine, cosines, and tangent. Okay, so we have trig identities. It's an equation involving trig functions that are true for all values for which every expression in the equation is defined. Tangent equals sine theta over cosine theta is true except for the angle measures that are written. Because cosine of 90, cosine of 270, and cosine of 450 are 0. Cotangent equals cosine of theta over sine theta is similar to this and therefore will be undefined when sine theta is 0. So basically we have these identities here that we can rewrite certain trig functions and it mean the same thing. Okay, so our first one is tangent of theta equals sine over cosine. Our Pythagorean theorem one, that will always work is cosine squared theta plus sine squared theta equaling 1. We can also rewrite these a little bit different. So if I wanted to do tangent on the bottom, that means I would have to flip-flop the right side, so it would have to be cosine of theta over sine of theta. So that's another option that I have. A couple options with this, I could subtract cosine squared theta to both sides. So I could have sine squared theta equaling 1 minus cosine squared theta. Or I could have subtracted sine squared theta and got cosine squared theta equals 1 minus sine squared theta. So there are some different options of using those two original equations and rewriting them in different ways that we can use to simplify our trig identities. So our first one here, what you have to do is you have to look at your identities and see what you can replace. So if I look at tangent, I know tangent also represents sine over cosine. So if I want to rewrite him, he is now sine over cosine. And then my big fraction bar, we have sine still on the bottom. Okay? If I want to rewrite that, that's the same as dividing is the same as multiplying by its reciprocal. So right now it's over 1. So if I keep my original, sine of theta over cosine of theta, I can multiply by its reciprocal. So if I flip him, he goes on the bottom. Okay, same thing on top and bottom are my sines, so what I have left is 1 over cosine of theta. Okay, so you're kind of looking to work it until you have just one sine, cosine, or tangent left, and then that's generally going to be the simplest form that you can go in. Okay, so my next one, I've got cosine and tangent. Well, tangent I know is sine over cosine again, so let's do that. So I'd be multiplying by sine over cosine. Okay, same thing on top and bottom because that's over 1. They can cancel. So my final answer is just going to be sine of theta. Okay, 3 here. 1 minus sine squared theta. If I look back at my originals here, 1 minus sine squared theta also represented cosine of theta. So I can go ahead and change that to cosine of theta, and it's still squared. So now I'm at this. Well, cosine over sine was one of my shortcuts. Okay, so if I go back to look at all my originals here, that's sine over cosine, but my other one, here's my cosine over sine, it represents 1 over tangent of theta. Well, if I have them both as squared, I need to rewrite my answer staying squared. So it'd be 1 over tangent squared theta. Okay, my next one here. I can check sine squared theta from my originals here. So sine squared theta equals this 1 minus cosine squared theta. That's not going to help me a whole lot. Okay, because then I'm going to have a 1 minus, and then I'll have to figure out how to separate fractions, and then it will get kind of ugly. But let's see if I have another one here. I have cosine of squared theta equaling 1, or cosine squared theta plus sine squared theta equaling 1. Okay, so actually I can take that top and make it 1. Now it's down to one term. Okay, number 5 here. What I could do is, right now there's a whole lot in there. I've got tangent squared theta. I could write it as a fraction. Right now I really don't want to write it as a fraction. Let's go ahead and separate what we have. So I'm going to put tangent squared theta over that whole bottom minus sine squared theta over that whole bottom. So now it's a little bit more separated, and I don't have to worry about a tangent and a sine being in the same top thing. So if I have the same thing on top and bottom, I can cancel. So now I've got 1 over sine squared theta minus, I can cancel 1 over tangent squared theta, which 1 over tan, our shortcut, was cosine over sine. And I still haven't done anything with that side. I don't want any minus signs because then I get some ugly fractions. But if I have a common denominator, I can actually bring this together. So now I've got 1 minus cosine squared theta over sharing that common denominator. And I'm pretty sure 1 minus cosine squared theta represented, too far. There's my 1 minus cos squared theta. It also represents sine squared theta, so I'm going to take them out. So my top now becomes sine squared theta. Still got the same bottom. If I got the same thing on top and bottom, they don't just become 0, it becomes 1. Because like 4 divided by 4 gets me 1. So sine squared theta divided by sine squared theta gets me 1. Okay, my next one here. Let's get them to have common denominator so that I can bring them together here. Because right now all I could do is make this a 1 minus sine squared theta, and that's going to get pretty ugly. So, to get them to have common denominators, I'm going to multiply him by cosine squared theta. So I've got 1 over cosine squared theta minus anything times 1 is going to be itself. And now they share that bottom. So since they share that bottom, we can bring them together. And 1 minus cosine squared theta represents sine squared theta. Anytime I've got a sine over cosine or a cosine over sine, it's going to represent some sort of either tangent or 1 over tangent. This one's going to get me my normal tangent, and since they're both squared, we need to make sure our tangent is also squared. Alright, my next one. I could rewrite this as my cosine over sine if I wanted to, or I could distribute. It doesn't matter which one you do. So if I send him in, I get sine of theta plus, he goes on the top, so sine of theta over tangent squared theta. Okay, rewriting this tangent squared theta, so I've got sine of theta plus our tangent squared theta. Remember, if I have a tangent, tangent is sine over cosine, so I'm going to represent it as sine over cosine in this. So I've still got the sine on top. This is like my big fraction bar that's separating them, and I changed him to sine squared theta over cosine squared theta. Remember, if I want to get it out of division, I multiply by its flip. So I've got sine of theta plus, I flip my fraction. So really we're multiplying by cosine squared theta over sine squared theta. Well, I've got 1 sine on top, 2 on bottom. So if I simplify him, I will have cosine squared theta over, I got 1 sine left in the bottom, but I still have stuff left. So let's go ahead and get them to be common denominators, see if we can combine them and simplify. So he needs a sine of theta on the bottom, so he'll become sine squared theta plus cosine squared theta, all sharing that sine of theta on the bottom. Well, sine squared theta plus cosine squared theta also represents 1. So I got 1 over sine of theta left. Okay, my next one here. What I could do, cosine over sine represents 1 over tangent. So it would become 1. I still got that 1 tangent on the bottom. He would become 1 over tangent, so he'd be sitting on the bottom. Tangent times tangent gets me tangent squared. And I dropped it down to 1.